Hi friends, welcome back. There are several tools that help us while tracing curves. As discussed in the previous sessions, first derivatives tell us whether a function is increasing or decreasing in small intervals and help us to identify local maximum and minimum. Second derivatives describe whether a curve is concave up or concave down in small intervals and help us to determine points of inflection and so on. In this session, we introduce another tool, asymptote, that helps us in sketching curves, especially when the curve is far away from the origin. The word asymptote is derived from the Greek word asymptotes, which means not falling together. The term was introduced by Apollonius of Perga in his work on conic sections, but in contrast to its modern meaning, he used it to mean any line that does not intersect the given curve. Roughly speaking, asymptotes are tangents that meet the curve at infinity. For example, consider the function y equal to e power x. We consider a point a on the graph of the function y equal to e power x and a line tangent to the curve at a. Since the choice of the point a is arbitrary, we can draw tangents at each point on the curve, and as we move the point on the curve away from the origin in the negative direction, that is letting x approaches to negative infinity, the tangent lines at these points come closer and closer to the x axis. Thus, x axis is a tangent that meets the curve at negative infinity, that is y equal to 0 is an asymptote to the curve y equal to e power x. We note that the x axis, that is y equal to 0, is a horizontal asymptote of y equal to e power x. As another example, consider the function y equal to 10 divided by x minus 5, where x is not equal to 5. We can draw tangent at each point on the curve when x is greater than 5, and as we move closer and closer to x equal to 5 from the right, these tangents come closer and closer to the line x is equal to 5. Thus, x equal to 5 is a tangent that meets the curve at infinity. Hence, x equal to 5 is a vertical asymptote. In the same example, we may draw tangents to the curve when x is less than 5, and as we move closer and closer to x is equal to 5 from the left, then also tangents approach to x equal to 5. Thus, x equal to 5 is a vertical asymptote both from right and left. There are asymptotes which are neither horizontal nor vertical. They are called oblique asymptotes. For example, the hyperbola x square minus y square equal to 1 has two asymptotes, namely y equal to x and y is equal to minus x. In fact, the equation x square minus y square is equal to 1 can be reformulated as 1 minus y square by x square is equal to 1 by x square, and as x goes to infinity or negative infinity, the right hand side of the equation goes to 0. Thus, we get 1 minus y square by x square is equal to 0, which gives y is equal to plus or minus x, getting two asymptotes which are neither horizontal nor vertical and hence oblique asymptotes. There are curves which do not have any asymptotes. In fact, for y is equal to sin x, there is no asymptote. Now, let us see the formal definition of an asymptote. An asymptote of a curve is a straight line at a finite distance from the origin to which a tangent to the curve tends as the point of contact recedes to infinity. We classify them into three classes. First one, vertical asymptotes, second one, horizontal asymptotes, and third one, oblique asymptotes or slant asymptotes. Vertical asymptotes. A line x equal to a is a vertical asymptote of the graph y equal to f of x if either limit x goes to a plus f of x is equal to plus or minus infinity, or limit x goes to a minus f of x is equal to plus or minus infinity. For example, consider the function f of x is equal to log x, which is defined for positive values of x. We have log x approaches to minus infinity as x approaches to 0 from the right, that is, limit x goes to 0 plus f of x is minus infinity. Thus, x equal to 0 is a vertical asymptote to the curve y is equal to log x. Let us now consider another example. F of x equal to x square minus 9x plus 14 whole divided by x square minus 5x plus 6, which is equal to x minus 2 into x minus 7 whole divided by x minus 2 into x minus 3, and which is equal to x minus 7 by x minus 3. Then limit x goes to 3 plus f of x is equal to limit x goes to 3 plus x minus 7 by x minus 3, which is equal to minus infinity, since the numerator goes to minus 4 and denominator goes to 0 from the right when x approaches 3 from the right. Thus, x equal to 3 is a vertical asymptote. Also from the observation that limit x goes to 3 minus f of x is equal to limit x goes to 3 minus x minus 7 by x minus 3, which is equal to plus infinity, it follows that x equal to 3 is a vertical asymptote. Hence, the line x equal to 3 is an asymptote both from left and right. But x equal to 2 is not an asymptote, as limit x goes to 2 f of x is equal to limit x goes to 2 x minus 7 by x minus 3 is equal to 5. As a third example of vertical asymptote, consider the equation y square into 2a minus x equal to x cube, where a greater than 0 is arbitrary. The given equation can be written as y square is equal to x cube whole divided by 2a minus x. And from this, it can be seen that as x goes to 2a, y goes to plus or minus infinity. So that the line x is equal to 2a is an asymptote to the curve given by the equation y square into 2a minus x equal to x cube. The graph and corresponding asymptotes for each value of a is shown in the figure. There are curves which have infinite number of asymptotes. For example, let y equal to f of x, where f of x is equal to tan x. Then limit x goes to pi by 2 plus f of x is equal to limit x goes to pi by 2 plus tan x is equal to minus infinity, and limit x goes to pi by 2 minus f of x is equal to limit x goes to pi by 2 minus tan x is equal to plus infinity. Thus, x is equal to pi by 2 is a vertical asymptote. In fact, for each integer n, limit x goes to 2n plus 1 times pi by 2 plus f of x is equal to limit x goes to 2n plus 1 times pi by 2 plus tan x, which is equal to minus infinity, and limit x goes to 2n plus 1 times pi by 2 minus f of x is equal to limit x goes to 2n plus 1 times pi by 2 minus tan x is equal to plus infinity. Hence, for each integer n, x equal to 2n plus 1 times pi by 2 is a vertical asymptote. Thus, there are infinitely many vertical asymptotes. Horizontal asymptotes. A line y equal to b is a horizontal asymptote of the graph of a function y equal to f of x if either limit x goes to infinity f of x is b, or limit x goes to minus infinity f of x is equal to b. For example, consider the function f of x is equal to e power x defined on the entire real line. We have limit x goes to minus infinity f of x is equal to limit x goes to minus infinity e power x is equal to 0. Hence, y equal to 0 is a horizontal asymptote to the curve y equal to e power x. As another example, consider the function f of x is equal to x square minus 9x plus 14 whole divided by x square minus 5x plus 6. Then we have limit x goes to infinity f of x is equal to limit x goes to infinity 1 minus 9 by x plus 14 by x square whole divided by 1 minus 5 by x plus 6 by x square, which is equal to 1. Therefore, y equal to 1 is a horizontal asymptote. Remember, we have already proved in the last session that x equal to 3 is a vertical asymptote. Thus, the given function has both vertical and horizontal asymptotes here. As another example, let f of x is equal to x plus 3 divided by x plus 2. We have limit x goes to infinity f of x is equal to limit x goes to infinity 1 plus 3 by x whole divided by 1 plus 2 by x, which is equal to 1. Thus, y equal to 1 is an asymptote which is horizontal. Further, for the same function, it can be also observed that limit x goes to minus 2 plus f of x is plus infinity and limit x goes to minus 2 minus f of x is minus infinity. Hence, x equal to minus 2 is an asymptote which is vertical. Thus, f of x equal to x plus 3 by x plus 2 has a vertical asymptote x equal to minus 2 and a horizontal asymptote y equal to 1. Let us now look into an easy method for determining vertical and horizontal asymptotes of polynomial equations in two variables. That is, equation of the form f of x y equal to 0, where f is a polynomial function in two variables x and y. Let y equal to k be a horizontal asymptote of f of x y equal to 0. Now, f of x y equal to 0 can be rewritten as g n of y times x power n plus g n minus 1 of y times x power n minus 1 plus etcetera plus g 2 of y times x square plus g 1 of y times x to the power 1 plus g naught of y equal to 0, where g naught, g 1 etcetera g n are polynomials in y. For example, for x to the power 4 y cube plus 3 x to the power 4 y square plus x cube y to the power 4 minus 5 x cube y cube minus x cube y square plus 6 x square y minus 2 x y plus 5 x plus 2 y minus 1 equal to 0 can be rewritten as 4 y cube plus 3 y square times x to the power 4 plus y to the power 4 minus 5 y cube minus y square times x to the power 3 plus 6 y times x square plus minus 2 y plus 5 times x plus 2 y minus 1 equal to 0. By dividing g n of y times x power n plus g n minus 1 of y times x power n minus 1 plus etcetera plus g 2 of y times x square plus g 1 of y times x power 1 plus g naught of y equal to 0 by x power n throughout, and letting x goes to infinity, we get limit x goes to infinity g n of y is equal to 0. Since g n of y is a polynomial in y, by the continuity of polynomials, limit x goes to infinity g n of y is equal to g n of limit x goes to infinity y. So, the above gives g n of limit x goes to infinity y is equal to 0. As y equal to k is the horizontal asymptote we are looking for, we must have y goes to k as x goes to infinity. That is, limit x goes to infinity y is equal to k, and hence g n of k is equal to 0. Thus, it follows that k is a root of the equation g n of y is equal to 0. Thus, if y equal to k is a horizontal asymptote, then k can be obtained by equating the coefficients of the highest powers of x to 0. Warning: the curve will have no asymptote parallel to x axis if the coefficient of the highest power of x is a constant or if it has no real root. Consider the example x square y square minus x square y minus x y square plus x plus y plus 1 is equal to 0. The highest power of x is x square and its coefficient is y square minus y. Thus, equating this coefficient y square minus y equal to 0, we get two horizontal asymptotes y equal to 0 and y is equal to 1. Similarly, we get vertical asymptotes by equating the coefficient of the highest power of y to 0. For example, consider x to the power 4 plus x square y square minus x square plus y square equal to 0. The highest power of y is y square and its coefficient is x square minus 1. Equating it to 0, we get x equal to plus or minus 1. Thus, we have two vertical asymptotes x equal to 1 and x equal to minus 1. However, note that the highest power of x is x to the power 4 and its coefficient is 1. Thus, we do not have any horizontal asymptotes here. As another example, we shall find the vertical and horizontal asymptotes of x square y square is equal to x square plus y square. The equation may be rewritten as x square y square minus x square plus y square is equal to 0. The highest power of x is x square and its coefficient is y square minus 1. Thus, equating this coefficient y square minus 1 equal to 0, we get two horizontal asymptotes y equal to minus 1 and y equal to plus 1. Similarly, the highest power of y is y square and its coefficient is x square minus 1. Thus, equating this coefficient x square minus 1 equal to 0, we get two vertical asymptotes x equal to minus 1 and x equal to plus 1. Oblique asymptotes. Let y equal to f of x be given by f of x equal to x square minus 3 whole divided by 3x minus 9. We perform actual division. Hence, we get y equal to x by 3 plus 1 plus 6 by 3x minus 9. The term 6 by 3x minus 9 approaches 0 as x goes to plus infinity or as x goes to minus infinity. Hence, it follows that y minus x by 3 plus 1 goes to 0 as x goes to plus infinity or as x goes to minus infinity. Geometrically, this means that the graph y equal to f of x eventually gets closer and closer to the line y is equal to x by 3 plus 1 as x goes to plus infinity or x goes to minus infinity. The line y equal to x by 3 plus 1 is called an oblique or slant asymptote to the curve, as the line y equal to x by 3 plus 1 is neither vertical nor horizontal. As observed in the previous problem, finding oblique asymptote of a curve is not much straightforward. So, let us analyze oblique asymptotes in detail. Suppose y equal to mx plus c is an oblique asymptote to a given curve, then m is not equal to 0. We shall now determine m and c, so that y is equal to mx plus c is an asymptote of the given curve. We first note that the distance from any point x naught y naught to a straight line ax plus by plus c is equal to 0 is modulus of ax naught plus by naught plus c whole divided by square root of a square plus b square. Now, let p is equal to p of x y be any point on the curve. We have the distance from p to the line y is equal to mx plus c is modulus of y minus mx minus c whole divided by square root of 1 plus m square. We need to determine m and c, so that this distance goes to 0 as x goes to infinity. This happens when limit x goes to infinity, y minus mx minus c is equal to 0, which means that limit x goes to infinity, y minus mx is equal to c. Now, limit x goes to infinity, y by x minus m is equal to limit x goes to infinity, y minus mx into 1 by x, which is equal to limit x goes to infinity, y minus mx into limit x goes to infinity 1 by x, that is equal to c times 0, which is equal to 0. So, that limit x goes to infinity, y by x is equal to m. The other constant c may be obtained from c equal to limit x goes to infinity, y minus mx. As an example, consider x square into x minus y plus ay square is equal to 0. The given equation may be rewritten in the form x cube minus x square y plus ay square is equal to 0, which is of degree 3. To find limit x goes to infinity, y by x, we divide this equation by x cube, so that 1 minus y by x plus a into y by x square times 1 by x is equal to 0. Let x goes to infinity, then we have 1 minus m plus a into m square into 0 is equal to 0. This gives 1 minus m is equal to 0, so that m is equal to 1. Let us evaluate c equal to limit x goes to infinity, y minus mx when m is equal to 1, that is c is equal to limit x goes to infinity, y minus x. As x square into x minus y plus ay square is equal to 0, we get y minus x is equal to ay square by x square, and hence c equal to limit x goes to infinity, y minus x is equal to limit x goes to infinity, a into y by x square, which is equal to a into m, that is a. Thus, y equal to x plus a is an asymptote. The figure is displayed for the value a equal to 2. As another example, let us find asymptotes of volume of Descartes. X cube plus y cube minus 3 a x y is equal to 0. Let y equal to mx plus c be an oblique asymptote. Since the given equation is of degree 3, to find limit x goes to infinity, y by x, we divide this equation by x cube, so that 1 plus y by x whole cube minus 3 a into y by x into 1 by x equal to 0. Let x goes to infinity, then we get 1 plus m cube minus 3 a into m into 0 is equal to 0. This gives 1 plus m cube is equal to 0, that is m plus 1 into m square minus m plus 1 is equal to 0. As m square minus m plus 1 is equal to 0 has no real roots, the only possibility is that m is equal to minus 1. Let us now evaluate c is equal to limit x goes to infinity, y minus mx when m is equal to minus 1. That is, c is equal to limit x goes to infinity, x plus y. We know that x cube plus y cube is equal to x plus y into x square minus x y plus y square. Thus, x plus y into x square minus x y plus y square minus 3 a x y is equal to x cube plus y cube minus 3 a x y, that is equal to 0. Hence, x plus y is equal to 3 a x y divided by x square minus x y plus y square, which is equal to 3 a y by x whole divided by 1 minus y by x plus y by x square. When x goes to infinity, we have y by x goes to m, which is equal to minus 1. Thus, we have c is equal to limit x goes to infinity, x plus y that is equal to limit x goes to infinity 3a y by x whole divided by 1 minus y by x plus y by x square, that is equal to minus 3a divided by 1 plus 1 plus 1, that is equal to minus a. Hence, y is equal to minus x minus a or y plus x plus a equal to 0 is an asymptote. In fact, this is the only one asymptote which is obvious from the graph of the folium x cube plus y cube minus 3a x y is equal to 0 for a greater than 0. It is worth mentioning something about the folium of Descartes. The curve was first proposed by René Descartes in 1638 to challenge Fermat's extremum finding techniques. Although he found the correct shape of the curve in the first quadrant, he believed that this leaf was repeated in each quadrant like the 4 petals of a flower. Descartes challenged Fermat to find the tangent line to the curve at an arbitrary point, since Fermat had recently discovered a method for finding tangent lines. Fermat solved the problem easily, something Descartes was unable to do. We have discussed 3 types of asymptotes, namely vertical, horizontal and oblique asymptotes, and the method of determining them. Hope you enjoyed the 3 sessions. Thank you. Bye. Have a nice